Hello everyone, I'm Bolun. I'm currently working in cost, but this work was done when I was in Beihang University and NYU with Zachary Ferguson, Teseo Schneider, Jiang, Attene, and Daniele Panozzo. I'm here to present our recent work, a large-scale benchmark and an inclusion-based algorithm for continuous collision detection. Here, the three figures are the comparison results of our algorithm with the state-of-the-art methods, and we will explain these figures later. Continuous collision detection, for short we call it CCD, is widely used in physical simulations. It's an important tool to guarantee two moving objects will not pass through each other. CCD algorithms report positives when collision happens, otherwise report negatives. To simplify the problem, people usually use two steps of linearization. First, triangle meshes are used to represent models. Second, assume the vertices of the triangles move along linear trajectories within a time step. After the linearization steps, the CCD between two objects can be converted to iteratively detecting collisions between two of the triangles. It can be obtained by checking if a vertex hit a triangle, or checking if two edges hit each other. Now a question comes up. What is the requirement for a good CCD algorithm? First, the CCD algorithm should not report false negatives. It means that the algorithm should not miss collisions. Secondly, the algorithm shouldn't report too many false positives, even if they are not as problematic as false negatives. And the algorithm should be efficient. However, this is not an easy task to develop a good CCD algorithm, because there might be some corner cases not covered by the algorithm. Moreover, even if the theory of the algorithm can be proved to be correct, using floating point arithmetic may introduce inaccurate results, leading to simulation failures, just like the example shown here on the left. Since verifying correctness is difficult, as it depends on the compiler and the hardware, we propose instead to introduce a large-scale benchmark to evaluate existing algorithms in an experimental way. To construct the benchmark, we extract around 60 million queries from the simulators, and we compute ground truths for each query symbolically using Mathematica. We also design a new format for reading, writing, and visualization. We use the benchmark to evaluate state-of-the-art CCD algorithms. These algorithms represent CCD problems into finding roots of different formulations. Some of them are using univariate formulation. It basically first checks if there's a time t that the four vertices of the vertex triangle or the two edges are coplanar. Then check at time t if there are intersections between the two objects. And during the process, we need to solve a cubic function with variate t. However, using univariate formulation is challenging for degenerate cases. Here we provide an example where two edges move parallelly. It will be difficult to process intersection check since there are infinite coplanarity time t. The other methods are using multivariate formulation, which are quadratic polynomials mapping R3 to R3 for both vertex triangle and edge cases. Checking if collision happens is equivalent with checking if the origin is inside the codomain of the mapping. But using floating point arithmetic may introduce computation errors, and to check the containment of the origin is not trivial. Here are the evaluation results of the state-of-the-art methods using our large-scale benchmark. For the methods using univariate formulation, we experimentally found that they report too many false positives, or report false negatives, despite their claims. And the two methods, RP and RRP, which use multivariate formulation, also miss collisions because they failed in checking if the origin is contained in the codomain. Among these methods, bisection interval root finding, IRF for short, is the only one that reports no false negatives and only a few false positives. But this method is not efficient enough. Bisection interval root finding method introduced by Schneider is illustrated in the following three figures, which show the first three iterations of the method. The green bar is called inclusion function of the function value g over interval I. Basically, the inclusion function ig is a conservative estimation of the codomain. Checking if the origin is contained by the function g can be conservatively estimated by checking intersections between the origin and the inclusion function. And the inclusion function is convergent to 0, which allows us to get more and more accurate root finding results by bisecting the interval I. Schneider implemented IRF using interval arithmetic to give conservative CCD results, but it is too slow and hard to give the time of impact. We introduced a new CCD algorithm inspired by IRF to obtain a correct and efficient CCD algorithm. We redesigned the inclusion function in a geometric way. We use forward error analysis to make the root finding conservative. We resort the searching order to find time of impact, and our method only uses floating point arithmetic. Here we show a 2D example of how to construct the inclusion function. The green part is the codomain of the multivariate CCD formulation. If the origin is inside the codomain, then collision happens. But we can also see that the shape of the codomain is very complicated. So we construct an axis-aligned bounding box of the vertices of the codomain as an inclusion function. We prove that the inclusion function is both conservative and convergent. Under floating point arithmetic, There might be rounding errors when constructing the corners of the codomain. We denote the four calculated corners A', B', C', and D' as blue dots, while the accurate position of them are denoted in red dots. Thus, we employ forward error analysis to compute the upper bound of computation errors epsilon, and we offset the inclusion function by epsilon to make it conservative. Our method has a very useful feature called minimal separation, which allows us to report collisions when the chip-shape distance of the two objects is closer than the user customized value d. Here we show an illustration in 1D. Instead of checking if the illustration function intersects the origin, we check if it intersects an interval minus d to d, which is in light green in this figure. In 3D, the interval will be extended into an axis-aligned cube. Then we bisect the interval and recalculate the equilibrium function to get more and more accurate results. What is more important is that it's almost free to enable minimal separation in our algorithm, unlike other methods, which usually requires more complicated calculation. We compare our method with 8 state-of-the-art algorithms. It can be seen that our method is accurate. It only reports a few false positives. Our implementation is correct, not only theoretically but passing the test in our benchmark. Our method is also comparable with state-of-the-art methods in efficiency. We integrate our algorithm into simulators. Here is an example where a torus falls on a fixed cone. The parameter delta is the solving precision of our method. Our simulation takes around 25 seconds, while using floating point root finder, which is a univariate CCD solver, it takes over 32 seconds to run the simulation. Here is an example where an octocat falls on the ground. The simulation time is around 63 to 67 seconds, and FPRF takes over 100 seconds. In this example, the simulation cannot proceed after the third frame because DSC reports false positives randomly. Using our method, the simulation proceeds successfully. In this example, the simulation cannot proceed because root party CCD reports false negatives, while our method enables robust simulations. There are a few limitations in our method. First, as a conservative method, our algorithm still has false positives. It will be interesting to see if our method can detect collisions exactly. Second, our minimal separation is defined using Chebyshev distance instead of Euclidean distance, which is more commonly used. Our method is designed for linear trajectories, but we have already added a new feature to support nonlinear trajectories. We use our linear CCD with minimal separation to form a conservative CCD for nonlinear rigid trajectories. In conclusion, we construct a large-scale benchmark for CCD. We evaluate existing implementations of the algorithms in an experimental way. We also introduce a new CCD algorithm, which is conservative and efficient. Our CCD algorithm enables robust simulations for triangle meshes. Thanks for your attention.